if I remember here in just a second, because we're about to see that. So you guys got pinged this morning. If you've got your alerts on Blackboard, you got pinged. I did post some announcements. So just a reminder about August 26th and 28th. Be prepared, a quiz might show up indiscriminately on Blackboard for those days, so I have something to monitor attendance with. But I will promise you the quiz will not be hard. I promise you the quiz will not be hard, but it will probably show up. I haven't put anything out there yet, but it will probably show up, and that will count for attendance. So be paying attention to Blackboard. I have also posted the NASA Scholars link for you guys. I posted it to the dates. We've had several students go to NASA over the last 3 years. And those dates for the application dates are, it opens up August 28th. And actually it's really kind of cool because the picture that's on the NASA site is one of our first folks that went, Brad Plunk. He's actually pictured right there on the NASA site, and that was one of our students that got to go. So those dates are open. And I have the link to the Bell program. We haven't talked a whole lot about it yet, but some of you actually heard Cody talk last spring when he came out. Those of you who know Peyton, Kristen, Riley Smith, and Brandon Hillhouse, they're all up there right now doing the program. But I did speak with Cody this morning, and Cody is likely to be coming out sometime towards the end of September, 1st of October. And I do know he did say for a fact that there will be a Bell experience either sometime during the semester or between the fall and spring semesters. There'll definitely be at least one. There might be two, but we just don't have all that information yet, but they're working on it right now. So for those of you who aren't familiar with the Bell program or didn't get a chance to hear what Cody had to say, that is a pre-engineering, it's an engineering program where you get everything that you need from the community college level. The two things that we currently do not teach that you end up taking as a class over the summer before you start through Ataskia Community College up in Minnesota. The program actually itself right now is through Minnesota State. But through the two classes that we don't cover here at NOC are circuits and multivariable calculus. But those of you who are taking multivariate or taking calculus actually cover the material. Minnesota State just doesn't recognize it right now. So you end up retaking a course, getting a really good grade for a course for material that you already have, which is really good. And it counts as extra hours for Minnesota State. So it's kind of a Benny. So that class isn't hard to really do through Ataskia. I teach dynamics early 6, and that's what I'm putting on the schedule. And dynamics is one of those classes that you have to have for the Bell program. But the idea behind the Bell program is you get your first 2 years through community college, then you do a 6-month, or it's not 6 months, but it's like 5-month boot camp, where you're doing a lot of professional development, learning how to learn through their online and distance learning module. And the idea is during that 5 months that you find a co-op to work at. And that co-op, you'll be working and going to school at the same time. And the idea is that it's a paid co-op, so you're getting paid while you're working as well as going to school. So that puts your engineering program at 4.5 years rather than a 5-year program. And it's a model that you're learning while you're actually working, so that when you leave school, you've got 2 years of work experience in addition to the coursework experience. Yeah.
You said anybody can do it?
Anybody can do it. Yeah. It's anybody can, and the cost is comparable to that of Oklahoma State. And they've worked it out so that financial aid is available. They've worked it out for a variety of different things. So and hopefully at the end, even though you've got financial aid, you've been working all along and you've hopefully earned as much as it's going to cost you to do it. And the co-ops can be with anybody. It's finding the co-op. So the people that the program's modeled off of Iron Range Engineering, which is up in Minnesota, and people have co-opted with people like Articat, DigiKey, if you're doing electronics. They've done with Caterpillar, they've done with mining companies, they've done a variety of different places, and they're really trying to work with the companies here in Oklahoma that you could be coming back and co-opting with somebody here. And they've co-opted, in fact, Cody Mann, who's been our contact all along, he did an international co-op. He went to Europe and did an international co-op for part of his co-op type experience. So it's more for those of us that learn better by doing. It's more designed to learn better by doing, and so that you're doing hands-on and you're doing your classes, so you're still getting all the theory work, but because you're actually in an engineering firm or you're actually working for a company, you get to see more of a practical application of why on earth am I doing this? You know, why am I doing it? And the other beautiful part is you're taking like 1 or 2 courses at a time. You're not taking 5 courses at a time. So when they've got it. So I posted the link so you can go look at it. And Cody encourages, if you're kind of interested, send an information request in. They've been really good about keeping in contact, haven't they, Madison?
Oh yeah, I get emails every couple months or so. They emailed me a couple times over the summer to see how things were going and what my plans are going to be this year.
Yeah. So it really is. Who all went with you for the experience last? Let's see, Hannah did. You went for the experience between the break. Who else went?
It was me, Hannah, Chase, and Kenny.
Okay. Yeah. So for those of you who, for some people the traditional approach is definitely the way to go. For some people, this new approach is the way to go. It's whatever is going to best fit you and your situation. But one of the really neat things is they're talking to community colleges all over the country. So your group that you come together with, maybe from the Delmarva area in the middle Atlantic, could be from Houston, could be from San Antonio, could be from, it's not just folks from Minnesota. And you guys went up there when it was cold and it wasn't too bad, right?
It wasn't bad at all.
And even if you are coming from a warm weather place and go up during the cold time, they loan you coats, so you don't have to. You don't have to have it. Just because that cold up in Minnesota, everybody thinks it's horrible. If the wind's blowing, there's no getting around it. Okay, if the wind's blowing, there's no getting around it. Cold is cold, no matter what you do when the wind's blowing. But I will tell you, I've been in North Dakota, standing outside of a building, having a discussion with people when it's around 0 degrees in short sleeves. It really is a different kind of cold. You don't want to be out there for 2-3 hours, but for 15 minutes while somebody's smoking a cigarette and you're talking to them about something, it's not too bad. Especially if you're standing in the sun, it's really not too bad. Because that's usually what scares people off. I gotta go to Minnesota, and you're like where they're at is like only about 20 miles from the Canadian border, so they're way the fool up there. All right, so I posted that information about the Bell program, so that's there. Also, just kind of keeping on track in WebAssign. Let it think about it for a second. I have posted the Chapter 18 pre-work, and I've posted Chapter 17 homework. So if you wanted to get started on Chapter 17 homework, you can. So it's all out there and it's available. And that all being said, we'll get started on some other fun stuff because we're going to finish Chapter 16 very quickly. Actually, we've already done all the theories of Chapter 16. Okay, it's doing the same thing here. This is interesting. There we go. technology's wonderful when it works. It's kind of frustrating when it doesn't. So we've been talking about simple harmonic motion. I actually went through the work portion last week, or last week. It feels like last week, let me tell you. It feels like last week. But I've actually posted the work portion on Wednesday, and the videos are posted. So the videos are posted. I will link them to my video playlist. I just haven't done that yet. But you guys do have the videos. They are posted. So what we finished with at the end of class on Wednesday is that the velocity of a simple harmonic oscillator at any point during the oscillation is going to be k over m amplitude squared minus x squared. And that's where we stopped. I did go through and we did get to, at least we wrote it down really, really quickly. And you guys can go back and look at the derivation in the text. But my omega for a physical pendulum is going to be mg, the radius towards the center of mass, or the distance to the center of mass, divided by the moment of inertia. And that compares to our omega from a simple pendulum, which is the square root of g divided by L, where that is the length. And that's kind of where we finished up at the end of class on Wednesday. So we're going to actually look at a physical pendulum and look at a comparison to see how this comes into play. And I'm going to do a biological example to actually show how it works as well. So let's take a physical pendulum. And in this case, I've got a physical pendulum that's, this part of the pendulum is going to be negligible in mass. Okay? That part of the pendulum is negligible in mass, and it's going to be it's going to be 0.5 meters. And at the end of my pendulum, I'm going to put down here a full meter-long rod. Right? It's a full meter-long rod, and this is going to be it's going to be a uniform rod. So we know, based on experience, because we did it in Physics 1 and we talked about it in Physics 1, we know from experience that if I have a rod and it's a uniform rod, the center of mass of that lovely thing, as long as it's uniform, is going to be halfway down the length. We also know that for a rod, that the center of mass is going to be along that axis there. So I can actually pinpoint the center of mass without doing anything mathematical. If you want to go ahead and prove it to yourself, you totally can. But we're going to use symmetry and the fact that it's a uniform rod to know where that center of mass is. So if I do that, I can put my center of mass on my system here, and the length to the pivot point is going to be 1 meter. Now, I know you guys use Chegg. Okay?
Yeah.
Yeah, I know you do, right? And if anybody ever wants to see my version of Chegg, you guys can stop by my office and see my version of Chegg. Because we didn't have the internet back then, I couldn't check it, okay? But I have these big, huge volumes of physics problems. Completed, solved physics problems. Our paper version of Chegg is what it was. And most of us had them, and we knew where to get them, and we shared just like everybody else. But this is one of those places where Chegg is going to kill you, because the only reason that all of a sudden these ones and things cancel out is because they were using nice, neat numbers. And Chegg doesn't necessarily tell you that we're using nice, neat numbers. And so this is one of those places that you'll go, well, I followed along exactly, and then you kind of figure out, wait a second, Chegg didn't tell me something. And this is one of those cases where Chegg didn't tell me something, because the length from the pivot point to the center is the same length as my rod is. So he said there's an easy way to get confused when I'm following along in Chegg and then everything disappears and we just don't know where it comes from. So if I do this, we can go back, and what we are going to do is we want to compare the period from the simple pendulum to the period of a physical pendulum. We're actually going to make that comparison. So if I go ahead and approximate this as a simple pendulum, and we know that we've been told that everything is going to behave just like all the mass was at the center of mass, we can do that period of the simple pendulum right away. That period of the simple pendulum is going to be 9.81 meters per second squared. I was writing down the frequency. Period is 2 pi. I was going, wait a second, the units are not going to be right. It's going to be 2 pi the length divided by gravity. Because I gave you the angular frequency, but if I convert it back to our period, this is what the period is. Because remember, angular frequency is 2 pi times the frequency, and that is 2 pi divided by the period. So if I'm solving for period, this is where I'm going to end up.
That's for the simple one.
This is for simple, yeah, this is for simple. This is still for the simple one. So if I go in here and I calculate it, I'm going to get the period is equal to 2 pi, and I'm going from the length here to the center of mass. So in this case, it's going to be 1 meter divided by 9.8 meters per second squared. And if I calculate that, that gives me the period is 2.01 seconds. That's just as if I'm taking the system as if it were a simple pendulum. But it's not, it's a physical pendulum. So one of the things that I know is I can use the parallel axis theorem for my moment of inertia. That's going to be the moment of inertia of the center of mass plus the mass to its new distance. Okay, I'm going to take the moment of inertia, I'm using the parallel axis theorem. To get there. Now this is a rod about its end. So I go to my handy dandy table in my book, or I go to my FE manual that's got the handy dandy moment of inertia depending on where I'm at. And I'm going to be spinning it about its end. So I look that up, and that's going to be 1/12, the mass of that times its length squared. Plus, oh, that should be squared. That should be MD squared. I knew I left out something. And that becomes MD squared. And this length is going to be from here to the center of mass. And this is where Chegg would get you, because that D happens to be 1 meter. Right? So it looks like it's the length of my rod, and it's not. It's actually the length of from here to there. Do that again. It's the length from here to there. So if I do this, I get 1/12 M1 squared plus M1 squared. And that's going to give me 13/12 M.
Can you scoot the paper a little bit?
And now you can see where Chegg might just go breezing right through and mess you up. So that's our moment of inertia of our rod that's now swinging about the end. So now if I go back and I look at my physical pendulum, so omega for my physical pendulum is square root mass G R for my distance, moment of inertia, and omega is equal to 2 pi times the frequency. Frequency is equal to 1 over 2 pi and that is equal to 1 over t, so I'm going to flip everything. T is now 2 pi square root our moment of inertia divided by mgr. And we figured that that moment of inertia is 13/12 m divided by mg. The r is my length to my center of mass, which in this case is 1. Masses cancel. Plug in the numbers, and I end up with 2.09 seconds.
Hold on a second.
And that compares with the simple one of 2.01 seconds. So if I were using this to keep my clock straight, my clock not going to work like I would with a simple pendulum. My period is longer with a physical pendulum than it is with the simple pendulum. We can do the same thing a little bit. I'm going to do essentially the same type of a problem, except this time we're going to look at a person's leg. Okay? We're going to look at a person's leg. And when I do this, we're going to assume that the moment of inertia of the leg is going to be 1/3 ml squared. Okay? Now, if I look at this person's leg, one of the other interesting things about our leg is if we actually look at a leg, okay, my artistic abilities aren't so hot, right? So there's a leg. So this is my leg. It's going to be an interesting leg, right? So we put shorts on this person, okay? Because otherwise it looks really bad, right? It's a really strange leg. But if I look for where the center of mass of that leg would be, we know that the center of mass is going to be not down here at the knee. It's going to be up in the thigh because the thigh is thicker than the calf, unless you got a Popeye type person. You know, there are some people's calves who are thicker than their legs, like the guy on the, what is it, Progressive Commercial? Is it Liberty Mutual? The one where he's customized his calves, he customizes his bike, and he customizes his calves, and his calves are really big. There's a commercial out there. And so if it's a normal human leg, right, my center of mass is going to be somewhere up in the thigh. Well, the problem where I took this was that from the hip joint to the center of mass, they said we can actually figure that out. We can say it's 3.7 meters. Okay? I mean, 3.7 meters. And this would be as if we're comparing it to the real thing. If we think it's rotating like a rod, and we can actually estimate that. We can actually get the mass of the leg. It's 6.5 kilograms. Now, this time we're actually going to calculate I using the physical pendulum piece versus I as if I were making it an assumption. So if I do the I as if I'm making it an assumption, this actually works out to be, and we actually have the whole length of the leg, and that's 0.88 meters. We can calculate this I, and if I do that, I get 1.7 kilograms meters squared for my moment of inertia. But we're going to use our data to calculate it from a physical pendulum point of view. So if I start out with the period is 2 pi I divided by mg, the distance to the center of mass. We're going to solve for I, so I is going to end up being the period squared mg, the distance to the center of mass, divided by 2 pi. If we do an experiment, we find that the leg swing period is about 1.2 seconds. So this R becomes my 0.37 meters. The mass is my 6.5 kilograms. My period is 1.2 seconds. And when I do that, this ends up being 0.86 kilograms meters squared. So the physical pendulum part means that my leg is not near as hard to swing as if it were just a big rod attached to my hip. Even with the weight shifted, that big rod attached to my head. So we get a big difference, and if I were trying to calculate that period of my leg rocking back and forth, I'm going to get a significant difference between my it's almost twice. So I get a big difference between looking at it from a physical point of view versus a simple point of view. But what's nice about physics, though, sometimes that simple one works out really well. Which is where you guys are starting to see when you guys are, for those of you that are taking thermodynamics and looking at the boundary conditions, one of the things that you have to always worry about, is it an ideal gas? Because if it's not an ideal gas, I'm going to have to worry about things that might happen like this. There are a lot of things that I can get away with just using the simple model for. But even in that case, let's look at our simple pendulum here. My simple pendulum, the difference was between 0.01 seconds and 0.09 seconds. Depending on what I'm doing, that difference may or may not be significant. But if I'm trying to do precision time calculations, that difference is significant. And if we think about the longitude problem, where I had to have a clock to know where I was from east to west crossing the ocean, a change of that over several days on each second could make me be off hundreds of miles. So it could propagate dramatically. So that's why we look at physical pendulums. Your book also looks at a torsional pendulum, but I am not going to worry about torsional pendulums right now. Torsional pendulum does this. I've got a disc, and we've all done it, that my disc will rotate back and forth in a twisting motion. Your book actually does a couple of examples with the torsional pendulum, but I'm not going to do that. All right, we're going to work another problem real quick, and then we're going to move on. So, I've got a system here where I have a spring. I've got a mass that is going to go down the slide. We're going to call this a distance x, and we're going to call the distance d, and we're going to call the compression of the spring x. We're given the following information. My angle, which is this angle right there, is going to be 20 degrees. The spring constant for my spring is going to be 540 Newton meters. The distance that we're going to go down is going to be 0.276 meters. The mass of my block is 2.49 kilograms. And it's going to be traveling at a velocity of 0.750 meters per second. And what we want to know is what is the distance the spring is compressed when the block momentarily comes to rest. Okay? All right. This is conservation of energy problem. So the energy before has got to equal the energy after. So the energy before is going to be the energy of the block plus the energy of the spring. That's the initial. It's going to equal the energy of the block plus the energy of the spring after. Well, the before part, we've got kinetic energy of the block, we've got its potential energy of the block, and we have the potential energy of the spring. Now, in the first part of this, the potential energy of the spring is 0 because it's at equilibrium, so I only have to worry about the block information. Afterwards, I got to worry about the kinetic energy of the block plus the potential energy of the block plus the energy of the spring. And depending on how I set up my system, I might be able to get rid of a couple other terms. But we do know that at the end, that when it momentarily comes to rest, that goes to 0. So I've already simplified this by getting rid of 2 terms. And if I'm creative, I can get rid of the 3rd term. If I'm creative, I can get rid of that term. Because what I can do is my potential energy at the block at the top is going to be mgh, where mg is d plus x. So now I can get rid of this term just by setting up my system to help me out. And this trick right here comes into play in lots and lots of engineering problems. So it's really easy to see this trick here because this is what I'm trying to find out, but I can eliminate it so I can kind of keep my system a lot cleaner by getting rid of that term and just setting up my boundary condition such that I can get rid of a whole term in my solution. So that leaves us with kinetic energy of the block, which is going to be 1/2 mv squared, and potential energy of the spring, which is 1/2 kx squared. So now when I write out my whole equation, I'm going to get 1/2 mv squared plus mg d plus x is equal to 1/2 kx squared. Which is a heck of a lot simpler than having 6 different terms in there. Now, d, right? D and dx, we can clean that up a little bit, and we can put that into this is along the plane, so I have to make sure that I have my sine and my angle in there, which I happen to leave out. So I've got my sine and my angle. So now what I'm going to do is just solve for x. And in the interest of time, we're going to end up with something that looks like this. K over 2 x squared minus mg sine of the angle x plus minus mv squared over 2 minus mgd sine of the angle has got to equal 0. Now I can start plugging in numbers, and I can use my quadratic equation. Quadratic equation, and ultimately you get x is going to equal 0.122 meters. Because I want to get a little bit further today. And I actually think you have a homework problem that looks a lot like this, if I remember right. Anybody got that far in the homework to know whether or not that's in there? I got shaking heads. I used to have one in there. Oh, let's do this one. So I guess we will start traveling waves next week. Oh well. So, I got a lake. And I got a buoy sitting in the lake. And the buoy is going to have a mass of 40 kilograms. It's going to have a cross-sectional area of 0.03 meters squared. We're going to push the buoy down into the water, 0.15 meters. Okay? And we release it. So what's the buoy going to do?
Gonna pop back out of the
It's
water.
going to bob up and down, right? It's going to bob up and down. And we want to know what will the period be. Okay, this is just a little bit different because we got to go back to fluids. All right, we got to go back to fluids. And remember that my buoyant force or my restoring force is going to equal to the amount of water displaced. Okay, my buoyant force is going to equal the amount of water displaced. So the volume of the water displaced is going to equal the area times the height of that volume of water displaced. So my buoyant force is going to equal the density of water times gravity times the area times the height. That's also going to equal the mass times the acceleration. And in this case, it's going to be the up and down motion. Okay? It's going to be the up and down motion. Now I'm going to rearrange this just a little bit. So I've got the density of water, gravity, area, height, divided by mass equals acceleration. Remember, Remember, we said when we did some playing with this on Wednesday that I could get acceleration was going to equal minus omega squared x. This is an oscillation equation. Well, if we change h to x, I get something that looks, these two equations are in the same form. They're in the same form. And that's going to help me out looking at this problem, because I can come back and equate this part to k over m, because remember omega is equal to the square root of k over m, and if I do it, if I square it, I end up with k over m. So this is going to act just like an oscillator. Now remember, the negative is dealing with which part of the bouncing up and down I'm doing, right? That's where the negative is coming in. So now if I do that, we already know that period from a couple other places, 2 pi over the square root of m over k. Well, now if I know that that's k over m, I can actually plug this in and I get that the period is 2 pi m divided by the density of water, gravity times cross-sectional area. And when I plug in the numbers, this gives me about 2.3 seconds. And the whole reason I do this problem is to show you that I can model these systems. This was a bobber in the water, but I can model that system as an oscillator. And we can do that modeling in a lot of different ways. And that's going to help us out in a lot of physical systems. And if we start doing atomic level things, infrared, when I'm doing infrared spectroscopy, I am looking at the vibrations of those covalent bonds. And I am exciting them to see what the oscillations are. We actually do this in microwaves because we want to get that excited in the oscillation so we can get those water molecules vibrating like crazy to generate heat. So understanding that I can model things as oscillators becomes really, really important and very, very useful. And being able to recognize that I have things that are in the same form becomes very, very useful for a lot of different things. And when we start getting into electricity and magnetism, we're going to see the same form of equations over and over again. And for those of us that have to relate things in our head back to mechanics, that becomes very helpful. Some of us will be able to relate things from electricity back to mechanics because your brain thinks that way. That's not my brain. But I know there are brains that think that way. So let's look at another one that we've experienced before. We've experienced that force is G M1 M2 divided by R squared. We've seen that before. That's Newton's law of universal gravitation. Not next week. Probably in about 2 weeks after that, we're going to see another one, and we've seen this one before because most of us have taken general chemistry. We get K Q1 Q2 over R squared. Both of these are field forces. Okay? Both of those are field forces. And I can do a general equation that a field force is going to be proportional to something 1 over R squared. This is Coulomb's law. And relates to electrostatics. This is Newton's law of gravitation. So we can get parallels and be able to model systems knowing that we can look at a variety of different things, just like if I have my oscillator equation and I happen to do an oscillator that looks like this, it's figuring out what this part of it is going to be, so that we can actually relate it back. And we get to see that an awful lot as we move through and derive a bunch of other equations. All right. Questions? Because I'm rapidly running out of time today. So that being said, I'll tell you the other part. Instead of starting traveling waves, I'm going to do something else. Go back to the computer. Maybe. Maybe we have to wake up the computer. There we go. There's part of it. Okay. Ah, there we go. Alright. My courses down here, we're in engineering physics. Go to course materials, week 2. I want an example of the Doppler effects, but I do not want a police car siren. I do not want a fire truck siren. I do not want any other, an ambulance siren, and I don't want a train whistle. Okay? I will also warn you, please be careful. On 2 different occasions, we've had some entertainment. Okay? We've had some entertainment, and it was over here in Enid, actually. Somebody was out doing a Doppler effect with their car horn, and the policeman showed up. They actually had to get on Blackboard to show them that it truly was a physics assignment, and they were actually assigned to come up with an example of the Doppler effect. So I will give you a heads up and a warning. So when you're doing your Doppler effect, or getting your example of your Doppler effect, just make sure and be aware of your surroundings. But you do have it clearly here that your physics professor has said that you got to do the Doppler effect. Okay? So I've had a couple of different occasions where people have been stopped about something. Alright? So just be aware. I do want an example of the Doppler effect. And primarily I want other examples other than just basically what we normally hear, because those are the ones that are used over and over again. I do have some other interesting ones that are kind of fun that when you actually start listening for the Doppler effect that you can get it. And so it's 25 points just to turn in an example of the Doppler effect, although you will not get credit for a train whistle, police car siren. You're not going to get credit for that. But you can get bonus points for figuring out the frequencies and the velocities associated with whatever your example is.
What's it do?
It is due September the 4th. It's due September the 4th. So any questions? We good? Remember, we don't have physical class on Monday or Wednesday, but you guys got plenty to do. You guys got plenty to do. And I will be back on campus on Thursday. I will respond to email, but I'm not guaranteeing how fast I can do it. Because I'm on plane most of tomorrow, and then I'm in meetings most of Sunday, Monday, and Tuesday. And then I'm in a meeting, and then on the plane on Wednesday, so.
Hey, Mr. McBride?
Yeah.
Can we skip here on Thursday if we need to do that thing with Armin?
Yes. Yeah. And actually, I will even, if you have to miss calc, I'll send in an excuse for calc.
Okay, all right, so do it Thursday morning. All right.
Yeah.
We'll look up to
Yeah, and I will send an excused absence for calc if you need it.
Okay, all right, thank you.